Hello and welcome to this video about linear algebra. And as always, many thanks to all the nice people that support me on Steady or PayPal. If you want a PDF version of this video, the link is in the description. Today's topic is the so-called PLU decomposition for matrices. You can see this as a supplemental video if you have already watched my video about the LU decomposition. In other words, this is just a generalization. However, L still stands for a lower triangular matrix, hence it's always a square matrix. But U in general is not a square matrix because it always needs to be of the same size as the original matrix we want to decompose. So what we want to get out here is the so-called row echelon form. Please note, for a square matrix this would be an upper triangular matrix, so we still denote it by U. And the last ingredient we have here is the matrix P, which saves all the row exchanges we have to do. Therefore, this is what we call a permutation matrix. Okay, now you know the three parts of the decomposition, so let's calculate them for an example. I want the matrix A to be a 4 times 5 matrix. There we have it, this is the matrix I have chosen for today. Now, if you want to start here with your common LU decomposition, you immediately find a problem. You can't use the 0 as a pivot to eliminate all the other numbers in the first column. Hence the first step you need to do is to go through the column to find a non-zero element to use as a pivot. Okay, we find it in the first row, therefore we need to exchange the first and the second row. Now a permutation matrix that exchanges row 1 with row 2 looks like this. It's simply a 4 times 4 identity matrix where we flip the two rows we are interested in. An important property is now, if we square that matrix, we get out our identity matrix. Hence, this is our first step, we just apply the identity matrix on the left. Then in the next step, we multiply one of the two matrices to the right, which means we exchange the two rows here. Afterwards, we have our pivot at the correct position. This means that we now can put the L matrix into the game. It should be a 4 times 4 matrix, so we start as usual with the identity matrix. And now we have to do the Gaussian elimination in the first column. So we want to generate zeros below the pivot, which means that we are already finished here. In other words, second row minus 0 the first row. And this 0 then goes into the L matrix. So this was easy, so let's go to the next number, which is 2. So third row minus 2 times the first row. And the multiple we subtract is the number that goes into the L matrix. Also not so hard, the only number that changes is the 5 that gets to a 3. And the last number in the column is the 1, so we subtract 1. And as before, this is the number that goes into the L matrix. And with that, we are finished with the first Gaussian elimination. Then in the next step we go to the next column and choose the next pivot, and we see it's non-zero, so we don't need any row exchanges here. Otherwise we do the same as before, we generate zeros below the pivot. In the first step we just have to subtract 1. And as before, this 1 goes immediately to our L matrix. On the other side we get a lot of zeros and a 1 here. And then in the next step we have to subtract 2 times the second row. This 2 then goes, as always, into the L matrix. And with that calculation, we are finished with the second column. Let's go to the third column. Okay, so this is not a pivot, but this is also not a pivot, so there are no pivots in the third column. This means that this column is finished, we have to go to the next column. However, there we also find a 0, which is not a pivot, but there is another pivot below. And with that we know what to do, we have to do a row exchange. In order to do that, we will insert the identity matrix again. So this is again a permutation matrix squared, where we have now the permutation matrix third row to fourth row. Of course, one of them we can apply to the right hand side again to get our row exchange. Indeed, there we get what we want, now we have the pivot at the correct position. However, the permutation matrix is not at the correct position yet, we need that on the left hand side. Therefore, in the next step, we will also add the identity matrix on the left hand side. So here again, we have the permutation matrix squared. Now you know, when we apply this matrix to the right, we will exchange these two rows here. However, if we apply this matrix to the left, we will exchange the corresponding columns. Nevertheless, this is exactly what we do in the next step. First, exchanging the rows looks like this. And afterwards, we exchange the columns, which results in this matrix. The good thing is, you see, we get again a lower triangular matrix. But don't oversee that this really changes the matrix L from before. The good thing is, you can remember the whole operation by just doing the row exchange in the blue part here. However, of course, now you have seen where it really comes from. Okay, now that everything is in the right order, we can continue our procedure. This means that we want to generate a 0 here, but it's already there, which means that we are finished with this column. In the next column we then find the pivot, which is here, but we don't have to generate zeros anymore. Indeed, this was our last step in the whole calculation. We have found the row echelon form here on the right hand side. Okay, so there we have our matrix U. And this is our matrix L. And the last part is what we still can multiply, but then we get our matrix P. We've reached our goal. Our matrix A from the beginning is given as P times L times U. And therefore we call this the PLU decomposition. Okay, I think that's good enough for this example. I hope you can now apply the whole procedure to another matrix A. And with that, thanks for listening and see you next time. Bye!